So in this video cast, we'll review chapters 1 and 2. Before we begin, make sure that you have some paper, a pen or a pencil, a calculator, and a book available. Pause the video now. Make sure that you have those things available to you right now before you continue. Make sure that you've got them in front of you so you can write down these notes and be successful in reviewing chapters 1, 2, and 3. Okay. We're going to begin on page 47 of your textbook. Page 47 of your textbook talks about something called average atomic mass. And the way to find average atomic mass of several different isotopes of an element is to find what's called a weighted average. And we're going to talk about how to find that weighted average and just look at a sample problem that's in the book. First of all, what is an isotope? An isotope is an atom that has the same number of protons but a different number of neutrons. For example, the element chlorine, if you look on the periodic table in the upper right-hand corner, has an atomic number of 17, which means that it has 17 protons. And there are generally 3 naturally occurring isotopes of chlorine. One is chlorine-35, and the other one is chlorine-36, and the other one is chlorine-37. Okay? What do these numbers mean? These are the number of protons right here. And notice the number of protons are the same. The number of protons tell you what the element is. This is the number of protons plus neutrons. Protons plus neutrons. And so by knowing this, known as the mass number, you can calculate the number of neutrons in each one. Okay? Now, to find the average atomic mass of this, we need to know what's called the percent abundance of each of these in a naturally occurring amount of chlorine. Now, I don't have the data offhand, but let's just choose a simple number. Let's say that this was 50% of naturally occurring chlorine. Let's say that this was like 10% of naturally occurring chlorine, and this would be like 40% of naturally occurring chlorine. I'd take these as a decimal, multiply them by their mass for each one, and then add them all together to get the total. So let's take a look at a sample problem. Sample problem's on page 48 of your textbook, and I'm just going to put this one in front of the camera here. It says 3 naturally occurring isotopes of silicon occur. Silicon-28, silicon, which has an average atomic mass of 27.9 something, silicon-29, which 44.68%, and has an average atomic mass of 28 something, and then silicon-30, which has an average 3.09% occurs naturally, has an atomic mass of 29.973, and these are all measured in atomic mass units, or AMU, to calculate the average atomic weight of silicon. I'm just going to quick toss the math up there, and then if you want to take more look at it in your textbook, you're more than welcome to on page 48. So the math would be silicon-28 has a mass of 27.97693 AMUs times a percentage of 0.9223, 92.23%, plus silicon-29, which has an average atomic mass of 28.97649 AMUs, and there is 4.68% of that. So 4.68% of that. Okay, and then add to that the last naturally occurring chlorine, which is silicon, which is silicon-30, which is 29.97377 AMUs, and there's 3% of that, so 0.0309. Multiply them together, and you'll end up with an average atomic mass of 28.0 atomic mass units. And to check your answer, you can actually look on the periodic table. Here's silicon, and if you zoom way in on silicon here, you can see that silicon's average atomic mass is approximately 28.09, 28.086. That's even more accurate. So, you know, we calculated what's the average atomic mass on the periodic table. And that's important to know because lots of times on the AP exam, they'll look at a different way of asking the same question. They might not tell you this. They'll say, what is the actual mass of this 4.68% isotope? And they'll give you the average, and then they'll ask you to find that. We'll look at a problem that happened a couple of years back that had you calculate something like this. Okay, that's the first part of chapter 2 and 3 to review. Second part, we talk about moles. You all know what the mole wheel looks like right here, and you should be able to convert from grams to moles, from moles to number of things, and back and forth. And then in chapter 10, we learned at standard temperature and pressure, you can use 22.4 liters per mole. And we'll see that this is mixed in with many, many problems. It's usually like one of the first questions that they ask, and it's usually fairly the easy one. Look for the easy questions to start with, see if you can get those right. Take a look at that mole wheel there. This is in your foldy or your really nice periodic table with lots of information. Make sure you know how to do those converting. Okay, so that's moles. Second thing. Next thing, empirical and molecular formula. Empirical and molecular formula. You usually see multiple choice questions like this, but I'm going to show you a free response question that happened just a couple of years ago. Empirical formulas are also known as the simplest formula. For example, CH2 would be an empirical formula because there would be 1:2 ratio between carbon and hydrogen. But, for example, C2H4 would be a molecular formula of this CH2. Could the empirical and molecular formula be one and the same? Yes, it certainly could be. And I'm going to show you an example problem of that from a recent exam as well really soon. Just know that that's the empirical formula. Lots of times what they'll do is they'll give you percent composition data. They'll give you percent composition data, and what they'll do is they'll tell you that a substance is composed of a certain percentage of carbon, hydrogen, and oxygen. For example, on page 97 of your textbook, they tell you that there's this substance called vitamin C that is 40.92% carbon. It's 4.58% hydrogen, and it is 54.50% oxygen. And then what they want you to do is find the empirical formula for this thing called vitamin C. Well, you can take a look on page 97 if you want in your book. Here's the actual sample problem. And you can see that what they do, first of all, is assume a 100-gram sample. Then they take that and convert each one to moles. And then they take and they divide by the smallest number of moles to get the ratio. And the ratio turned out to be 3:4 to 3. So the empirical formula for vitamin C was C3H4O3. Take a look on page 97 if you don't remember that empirical and molecular formula part. They actually lay it out really nicely there, and I'll show you one in just a second. Next thing to review from chapter 2 and 3 are a little bit of stoichiometry and stoichiometric ratios. Knowing your stoichiometric ratios from your balanced chemical equation is key. So for example, H2 plus O2 yields H2O. A balanced chemical reaction would have 2 hydrogens and 2 waters in here, and you would say that for every 2 of these, there are 1 of these. And finding these ratios in the equation is actually quite challenging sometimes for people because they ask it in a picky way. Going on further to, for example, chapter 5, remember if they tell you that this is negative 100 kilojoules per mole for the reaction, for every 2 moles of hydrogen, the ratio is there are 100 kilojoules of energy released. For every 1 mole of oxygen, there are 100 kilojoules of energy released. And you can get these kind of ratios from a thermochemical equation, 2 to negative 100 reaction there, ratio there as well. So stoichiometric ratios. Once you get into these things called moles, lots of times what people will want to know, and they didn't do this until chapter 10, is something called the mole fraction of a mixture, usually of gases, and this mole fraction is symbolized by this giant letter X. And all that means is part divided by the whole thing. So for example, let's say you had a container, and inside of this container you had 3 different gases. One of them was oxygen, one of them was hydrogen, and one of them was chlorine, for example. And let's say that there was 1 mole of this guy, 2 moles of this guy, and 1 mole of this guy. Or, more commonly, they'll give you grams and have you convert. Then to find the mole fraction of oxygen in here, you'd take the part, 1 mole of oxygen, and divide it by the whole thing, which would be 1 plus 2 plus 1, which would be 4. So the mole fraction would be 0.25. And what's cool about mole fraction is that it doesn't have any units on it as well. Okay? Next thing to review from Chapter 3 are what are called limiters, or limiting reagents. Limiting reagents are the thing that runs out in the chemical reaction. So for example, let's say we had that H2 plus O2 yields H2O reaction back up here again, and let's say I had 1 mole of each reactant. Well, which one would run out before I'd actually be able to produce as much H2O as possible? To determine this, the quick and dirty way is to simply take each and pretend to divide it by its coefficient. Don't actually do the math. Just say, hey, if I divided it by its coefficient, which one would be the smallest? The smallest one would be the one that's used up the quickest, and this would be a half, this one would be 1, so H2 would be my limiter. Now, another way to tell this really quickly is just to take a look at how much would be produced by each one. So I could say for every 1 mole of H2, how much H2O would I produce? Well, put H2 in a position where it can cancel, and there's a 2 to 2 ratio right there. So I would produce 1 mole of H2. Now, if I used O2, for every 1 mole of O2, for every 2 H2Os, there would be 1 O2. How much would I produce? Well, I'd produce 2 moles of O2. Which one would produce the least amount? That's the one that limits my reaction. So either one of these ways is okay in determining the limiter. I personally favor this one because it's quick and dirty and maybe takes a little less thinking sometimes too. Just say, if I divided it by the coefficient, which one would end up being the smallest? In this case, H2 would be my limiter. Okay? The next thing to review from Chapter 3 are things called hydrated compounds. Hydrates are substances that have a dot and a number and some H2O connected to it. For example, copper sulfate usually exists in a form copper sulfate pentahydrate. It means there are 5 waters connected to the crystal of copper sulfate. The dot does not mean multiply. The dot does not mean multiply. It means that there are 5 waters connected to the copper sulfate. And this actually gives you I guess in effect, a stoichiometric ratio, saying for every 1 copper sulfate, there are 5 waters. For every 1 copper sulfate, there are 5 waters. Okay? Now, there are other ones too. So, for example, let's say it's calcium sulfate dot 2 H2O. Well, now there's 2 waters for every calcium sulfate. Or you could get really picky and you could say there are 4 hydrogen atoms inside of this entire calcium sulfate dihydrate molecule, I guess you'd call it, or particle would probably be better. Finding the amount of water that's connected to a hydrate is usually done in an experiment where you actually take this substance and you heat it. When you heat it, you drive off the water, and you can calculate how much water is being driven off by knowing the original mass, and then you can subtract from it the mass that's after it's been heated for a while. Now, you want to make sure to heat it several times in a row to make sure you've driven off all the water off, and not heat it too much so you'd like decompose it or actually like melt this and turn it into its ions or something like that. So heating it steady on a decent heat drives the water off and makes it become evaporated, and then you'd get what's called a dehydrated compound. And you can figure out how much H2O was left off. And this is a common question in the AP exam in the past number of years, where they'll say, what is the formula of the hydrated compound? And they'll want you to do mass original and mass heated, et cetera, to figure out how much water was driven off. I'll show you an example of one of those in just a little bit as well. All right? Last one, Chapter 3 to know, is something called combustion Analysis. And in the 10th edition of Brown LeMay Burston, this takes place on page 99. Page 99. And what this one does is take something usually made of carbon, hydrogen, oxygen, maybe some nitrogen, maybe some other molecule too. And then what they do is they burn it. And when they burn it, of course, they burn it in oxygen. And the products of these types of combustion reactions are always carbon dioxide and water and maybe something else. But usually what we assume is that the law of conservation of mass takes place and all the carbon is converted to carbon in carbon dioxide. All the hydrogen is converted to hydrogen in water. And then from subtraction, we can find how much oxygen was in that molecule or how much nitrogen was in that molecule or whatever it was. Convert it to moles, divided by the smallest, and then we have the empirical formula of that substance. A really good example problem on page 99 of your textbook has a person determine the empirical formula of something called rubbing alcohol. It's got carbon, hydrogen, and oxygen in it, and they say that they have a 0.255 grams of this isopropyl or rubbing alcohol. And they say when it's burned in a combustion analysis device, 0.561 grams of CO2 are produced, and 0.306 grams of H2O are produced. The steps to this, as I said before, is to first, when in doubt, convert to moles. Okay? This would be moles of CO2. This would be moles of H2O. 18 grams in 1 mole of that. 44 grams in 1 mole of that. Next, convert to how many moles of just carbon we have and how many moles of hydrogen we have. And in H2O, this is the tricky part, there are 2 hydrogens. Notice this small little 2 down here. And in CO2, there's 1 carbon. And then lastly, convert to grams of carbon and grams of hydrogen. And of course, there's 1 gram in 1 mole of H, that's from the periodic table, and there are 12 grams in 1 mole of carbon. When you look on the periodic table, you can look at its atomic mass right here. Carbon's 12, hydrogen, of course, is 1 up here. This gives you your mass of carbon, this gives you your grams of hydrogen, and I can subtract those from the original mass that I had, which was 0.255 grams. After doing that subtraction, I also get my grams of oxygen. Now, it's just like an empirical formula problem. Convert to moles and divide by the smallest. Want to look at one of these types of problems? Sure. Page 99 in your textbook. 99 and 100 have several sample problems in there, and I'm going to show you one from a couple of years ago that was on the AP exam, just like that in a second as well. So I've been talking about these are the important things that are kind of emphasized on the AP exam to review. Right now, what I'm going to do is I'm going to go through from the past 6 years' exams, and I'm going to go through problems that involve percent abundance, the mole wheel, empirical formula, stoichiometric ratios, mole fraction, limiters, hydrates, and a combustion analysis problem. So if you need a break, pause the video now. Otherwise, I'm going to go through the problems. I'm not going to do every single little part of it, but you'll see where it came from and what the expectations were for that year. And then we'll go through the answer. We'll just go through the answer guide, and you can see what they expect for answers, and then you can try some of these problems in class. Not these exact problems, but some of these that'll be similar as well. So let's go in order. First one right here is a percent abundance question. This was question 2 from 2007, Form B. Question 2 from 2007, Form B said, the average atomic mass of naturally occurring neon is 20.18 AMUs. There are 2 common isotopes of the naturally occurring neon, as listed in the table below. And you can see right here that one of them has an atomic mass of 19.99, and the other one is 21.99. Using the information above, calculate the percent abundance of each isotope. So what they had you do here now was they had you set up the same type of thing that I had before, where it was here is the average atomic mass from the periodic table. And then they said, okay, one of them is 19.99 times its percent abundance. The other one is 21.99 times its percent abundance. Now, you could have called this X and this Y, but remember both percentage abundances have to add up to equal 100%. So they called one of them X and the other one minus X. And then they did a bunch of algebra right here, and they found out that 90.5% was neon 20 and 9.5% was neon 22. Told you they'd come up with a different way to ask the question other than just was on the, just a standard old problem from the book. Take a look back at 2007 if you want to see that. Okay, next they look specifically at neon 22 and they ask a grams to moles to molecules question. Actually just a grams to moles question. They say calculate the number of, grams to moles to atoms, I'm sorry, neon atoms in a 12.55 gram sample of naturally occurring neon. Okay, so first I take my grams and I convert it to moles, and notice right here when I convert to moles, the mass that I use is 20.18. Why don't I use this mass up here? One of these two masses up here. Remember, these two masses were just for these isotopes right up here. Okay, so I'm going to take the naturally occurring neon's atomic mass, which is 20.18. I can find that on the periodic table, 20.18 right here, and convert it to moles of that. Then I knew that 9.5% of naturally occurring neon is neon 22. So I multiply it times that 9.5% as 0.095. And then in 1 mole, there are 6.02 times 10 to the 22. And you can see that they ended up with that answer right there. Notice the points right here. 1 for the correct molar mass, knowing that it's naturally occurring neon. So you had to use this molar mass right here. 1 for using the 9.5% right here. And then 1 point is earned for the number of atoms right here using 6.02. Notice how 3 points were given for that problem, and all it was a gram to molecule type question. Okay? On the next page, you can see how they absolutely love to, on AP exams, to ask questions that span over more than one chapter. They don't stick with a chapter 2, 3 question now. They go to a chapter 6 question where they use lambda equals C over nu, and they ask you a nanometers question. Here they do a E equals H nu type question, and then they ask you an energy question down here too. So you can see just from this example, I'm not going to do this now because we're not reviewing chapter 6 and 7, but you can see that they love to plug those things in. Even though it's just one question, they're going to plug several chapters worth of stuff in there. All right, next question comes from 2011, Form B, question number 3. The very, very first question is an easy gimme question where it says, answer the following question about glucose. What is the empirical formula of glucose? So all you have to do is look at the molecular formula right here and say, what's the simplest whole number ratio? And there it is, CH2O. Okay? Next question, they say, is that a 2.5 gram sample of glucose and excess O2 were placed in a calorimeter after the reaction was initiated. They released 39 kilojoules of energy. I guess I should zoom out a little bit so you can see that. And then the very first thing you need to do, grams to moles. Grams to moles. And then use the mole to mole ratio right here between the 39 kilojoules of energy that's released and the amount of energy that we have. So there's another example of how this doesn't remain as a chapter 3 question. They go right on and ask a chapter 5 question where you got to do kilojoules per mole right away. And if you actually scroll down on this, now they're going to ask you a G question. G equals negative RT natural log of K. Next question, 2011, Form B, question number 2. This one right here gives you a sample of methanol, and they put it in an evacuated tank, and then they give you a balanced chemical equation right here for the decomposition of it, and it tells you how many moles of carbon monoxide are there at a particular temperature. So the first question they ask is a little stoichiometric ratio one, where they say calculate the moles of H2 in the tank. So here we've got the number of moles of CO in there, and then we've got an H2 moles right here. Notice it's a 1:2 ratio. So I take that 6.3 moles, multiply it by a ratio of 2 to 1, and I end up with 12 moles right there. Stoichiometry, right there, easy gimme question. Okay, next they ask a moles to grams question. So it's calculate the number of grams of methanol remaining in the tank. So once again, a stoichiometric ratio problem right here. CO to CH3OH is a 1-to-1 ratio right here. So you get 6.3 moles of that are reacted. Okay. And then this was the initial amount of CH3OH in there. So you subtract the amount that was reacted to find out how much is remaining in there, and then convert from moles to grams. So look, a nice little stoichiometry problem in there. Last one they say, what is the mole fraction? And remember, the mole fraction is part divided by whole. Well, you know the number of moles of hydrogen in there from part 1, and then you need to divide it by the total number of moles. So part divided by whole. And then you can see that they love to mix in things besides chapter 3. They throw in a chapter 10 pervert problem right here to find the pressure inside the tank. And they go on to ask a couple more questions in that are a little bit outside of this chapter, but it's more chapter 10 gas laws type problems. Here we go, 2009. 2009, question number 3. A sample of methane gas, 25 gram, is placed in a vessel containing a number of moles of chlorine. Okay, they give you a balanced equation right up here at the top. First question, identify the limiter. Remember I told you there was going to be a limiting reactant problem? First thing, convert to moles of methane. Now you have your moles of chlorine and your moles of methane. How do I determine the limiter? Take both and divide them by their coefficient. So CH4 moles would be divided by 1, chlorine would be divided by 2. Turns out that the chlorine is the limiter. Chlorine is the limiter. That's the one that ends up being the smallest when you divide it by 2. Notice they also say 1 point is earned. Alternative methods are accepted because they don't like my just divide by the coefficient to figure it out, but they're acceptable. Next, calculate the total number of moles of this CH2Cl2 in the container after the limiting reactant has been totally consumed. So now take your limiter and stick the stoichiometric ratio between it and the CH2Cl2, a 2-to-1 ratio. Notice here's my 2-to-1 ratio, and I end up with 1.29 moles. And then they go in and they love to do this. They ask a chapter 5 question. Actually, it's a chapter 8 because they ask you for a bond enthalpy, breaking the Cl-Cl bond. So don't be shocked by that. Be okay that this is chapter 3 stuff, and then it jumps right away to a chapter 8 bond enthalpy type question. We'll review those a little bit more, and then they stick in a nu equals E over H type problem down here too. So become familiar with that. Understand that, hey, they want to mix up the chapters on you, but get the easy ones. Get the gram to mole molecule. Get the limiters. That kind of stuff. Next one, 2008 question 2. Here's a great lab type question they love to ask. Here's an experiment to determine the moles of water in this hydrated compound, MgCl2.NH2O. What do they want to know? Of course, they want to know N. How many moles of water are attached to that MgCl2 crystal? So they've got a mass of an empty container. They got a mass in the sample. Then they heat it. Okay, and you can notice that the mass stays similar here at the end. Once you get 2 similars in a row, you know you've heated it enough, and therefore you've driven off all the water. So first of all, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times. No additional mass was lost during the third heating, indicating that all the water hydration had been driven off. Now some people get in a panic mode here because they look at this and they'll say, yeah, but this and this are off by like 0.001 grams. You know what? In a lab, that is close enough, okay? That is close enough. Next one, calculate the total number of moles lost when the sample was heated. Moles of water lost. So the mass of the water lost needs to be found first. So here's your starting mass. Here's your ending mass. 1.848 grams were driven off. Now you need to take that and convert it to moles. 18 grams in 1 mole. Here's my moles of water. So once again, convert from grams to moles. Simple problem, simple point. Determine the formula of the hydrated compound. Now it becomes an empirical formula problem. I have my moles of water right here, okay? And now I need my moles of MgCl2. So I take my mass of dehydrated MgCl2, convert it to moles, and now I take and I get a ratio between water and MgCl2. MgCl2 is the smallest, so really what I have is I'll write this out because some people are frustrated by this, 0.1026 moles of H2O, and I have 0.01, that's a 1, 712 moles of MgCl2. Okay, to find this now, divide by the smallest. Find this now, divide by the smallest. Well, my smallest is MgCl2, so I'll end up with 1 MgCl2, and I end up with 6 H2O. So my formula ends up being MgCl2 dot 6 H2O. Remember, the dot does not mean multiply. Okay, on the back side here, they'd love to do this. On the back side of this, now they tack in and they start asking questions about other stuff, more lab type questions. And I'm going to go through them because you're going to get a lab question. Probably not like this, but some kind of lab question where I ask you some weird questions about what you do in the lab. A different student heats the hydrated in an uncovered crucible, and some of the solid spatters out of the crucible. This spattering will have what effect on the calculated mass of the water lost by the hydrate? Justify your answer. You know that they love that word. The calculated mass or moles of water lost by the hydrate will be too large because the mass of the solid that was lost will be assumed to be water when it actually included some MgCl2 as well. So 1 point for the answer and the justification. So notice that when stuff spatters out, you got to be able to figure out, oh yeah, we not only lost some water, but we also lost some actual compound. In the second experiment, the student is given a 2.94 gram mixture containing anhydrous MgCl2 and KNO3. To determine the percentage by mass of MgCl2 in the mixture, the student uses excess AgNO3 to precipitate it. The chloride ion is AgCl2. Now, starting with 2.95 grams similar to the mixture dissolved in water, briefly describe the steps necessary to quantitatively, that's numerically, determine the mass of the AgCl precipitate. First of all, add excess AgNO3. Okay, excess. You don't want that to be your limiter because you want to get all of the chlorine out. Separate the AgCl by filtration, wash the precipitate, and dry it until there's no more water left, and then determine the mass of AgCl by difference. So that means subtract it from the original. Okay, then notice how many points there were. The student determines the mass of AgCl precipitate to be 5.48 grams. On the basis of this information, calculate each of the following. So here's a grams to moles one again. And here's a moles to the mole to mole ratio, and you get how many moles of MgCl2. Then they have them find you the mass of MgCl2 in the original mixture. This was a tough problem for a lot of kids. A tough problem for a lot of kids because they couldn't think in terms of what would I really do? What would I really do in the lab? And then they couldn't put any of that into grams to moles to percentages. I'd take a look back at that one, 2008, number 2. Be prepared for something like that. All right, last question to go over for the review of Chapter 3. This is 2006, question number 3. Answer the question that relates to the chemical analysis of compounds. So here's one that's got C, H, N, and O. It's burned. Hey, combustion analysis. Oh, yippee. Okay. And you get this many grams of oxygen. Oh, in excess oxygen, grams of carbon dioxide. The combustion analysis also showed that the sample contained this many grams of hydrogen. So they give you some information. They give you more information than what you get in a normal combustion reaction. Determine the mass in grams of carbon in the sample. So first thing to do is take your grams of carbon dioxide, convert it to moles. Then for every 1 mole of carbon, there's 1 mole of carbon dioxide because it's a 1-to-1 ratio right here. 12 grams in a mole, so there's your grams of carbon. That was worth 1 point. Just 1 point for finding that. When the compound is analyzed for nitrogen content only, the mass percent of nitrogen is found to be 28.84%. Okay? Determine the mass in grams of nitrogen in the original 1.2359 gram sample. So if I'm given a mass percent of nitrogen and I know the total grams of the sample, just multiply with the percent times the grams, and now I know my grams of nitrogen. Okay, can you see where this problem's going? Because now you have grams of carbon, you have grams of nitrogen, and up here you had grams of hydrogen. And notice this thing was made up of 4 different things. You now have 3 of those. Guess what they're going to have you find? Determine the mass of grams of oxygen in the original compound. So now you take the 3 circled things right here, subtract it from the original mass, and of course that's your mass of oxygen in there. Okay? Determine the empirical formula. Now it's going from grams to moles, and then dividing by the smallest. Divide by the smallest right here, and that's on the next page. Divide by the smallest, and you end up with a 4 to 5 to 2 to 1 ratio, and you get this empirical formula right here. Okay, they go on, and now they start asking some questions that are Chapter 10 questions about a different compound, but they love to toss things together like this, and they start to try to confuse you. And this one's got a density equation with it too, so you got to remember either PV equals nRT to find that, or you can remember that military police over rapid transit is equal to density, and then that's an easy one to solve. But that's a Chapter 10 reviewer. This ends the review of Chapter 3. During class now, you'll be doing a bunch of these types of problems once again that include percent abundance, mole wheel, empirical formula, Stoichiometric ratio, maybe some limiters, some hydrates, some combustion analysis stuff. And you need to become good at those and good at, seeing through how they'll ask you a little bit trickier question that might, just be slightly different from these types of problems already. Good luck with your Chapter 3 review.